Well, we switched to English because we're extremely honored. I practiced this name many times, I hope it will go well, to introduce Xiaosi Gu. Dr. Insel, yesterday, introduced us in the world of digital phenotyping and digital measurements. I think one of the first vistas. I could not find a better translation for vergezicht. I hope vista is close enough. So that we take on another vista today, of these 5 vistas that we formulated, that of computational psychiatry. And before I give the floor to Dr. Gu, I want to introduce you a little bit that computational psychiatry is very broadly defined, and for many of you probably a new field, but very important. It basically encompasses 2 complementary approaches. One is really data-driven and has the appeal of machine learning to predict or to select treatments or improve selection. The other one is theory-driven, which means it is really initiate on prior knowledge or a model, that you can actually test how the brain computes or processes underlying mechanisms into cognition, sensory, or motor information processing, which requires another level of abstraction and analysis, which will be addressed by Dr. Gu. She's one of the foremost researchers in this field, and has recently become the director of the Computational Psychiatry Unit of Mount Sinai Hospital, under the guidance of somebody we very well know. Her research examines the neural and computational mechanisms underlying human beliefs, emotions, decision-making, and social interaction in both health and disease through this synthesis of theory in neuroscience, cognitive science, and behavioral economics. So embrace yourself for a very interesting and innovative lecture fully in the theme of our future. Welcome, Dr. Gu.
Thank you. Okay. Hi. Thank you very much for your hospitality. I've had great fun already in the past 2 days. Thank you again for inviting me. Also, just to reiterate a point made by Dr. Insel yesterday, that I think after I go back, I will urge all the conference organizers to model after you guys, because all the conferences elsewhere, like including America and also I think the UK, are just way too boring compared to this one. So thank you for your inspiration. Okay. So. My talk today will be mostly based on 2 parts. Part 1, I would really like to give a brief introduction on computational psychiatry. I think there's still a lot of sort of myth around this term, although it has become a buzzword even in the pop media. And then for part 2, I will briefly discuss the work that's going on in my lab. Okay. So again, thanks to the nice introduction by Dr. Insel yesterday, I don't think I have to repeat the fact that psychiatry research is facing a crisis. And obviously the question we have in our mind is, why is that the case? We've dedicated a lot of resources and manpower to the study of both the brain and the human mental processes. Right? We have experts that focus on either this physical space to study things like neurons, other cells in the brain, neural circuits, synapses, neurochemicals, as well as genetic information. Right? So these are the sort of the more observable and more physical aspect of the human mind. On the other hand, we have obviously thousands of years of interest in the mental space per se, right? So philosophers, psychologists, and psychiatrists, before the era of biological psychiatry and before the era of cognitive neuroscience, I think have mostly been thinking about mental space, things like memory, attention, emotion, these terms. And the difficulty of studying this space is that obviously it's more invisible, right? So we always try to find sort of either behavior or neural proxies to measure these things. And, we've had biological psychiatry and cognitive neuroscience for several decades now. So the question is, why haven't we still made much progress? I think this question mark here can partially be sort of addressed by a newer approach, actually really a sort of a revolution in the field now, which is to think about these processes in terms of computations, right? So there are specific neural signals that actually compute rather than just correlate with the mental processes we're interested in. And I think understanding this would be really, hopefully, one of the biggest take-home messages you'll get today. Okay, so what does computation mean? That's a tricky question. And to answer this, I would have to cite actually David Marr's work. So David Marr was a vision neuroscientist who primarily worked at MIT when he developed this what's called 3 levels or tri-level of analysis theoretical framework. And the theory says this: to understand any intelligent system, we have to understand the system from 3 distinct levels. At the very highest level is what we consider, or what he calls, computational, and that really describes the goals of the system, right? So what is the goal of the human brain? I mean, it could be seeking food, seeking shelter, seeking love. These are distinct goals. What is the goal of an artificial intelligence system, like AlphaGo? And I'll talk a little bit about that later, right? Well, the goal is very simple. It's to win the game Go. So to understand the goal of the system is actually quite important. And below that is what he considers the algorithmic level. And this is really to describe the representations of the brain. So what representational processes, what algorithms does the brain use to achieve its goal? And lastly, at the very lowest level is what he considers the physical realization or implementational level, right? So these are in the brain space. These are the things that we are maybe more comfortable with these days. So when we talk about neurons or circuits or neurotransmitters, fatty acids, and genetic information, these are the biological substrates, the physical substrates that help us to implement the goals and algorithms. And obviously, computational psychiatry aims to connect these different levels in order to understand mental function and dysfunction. And an easier way to understand this is a really old analogy, actually, right? Again, if you have any computer science background or just have basic understanding of how a computer works, this is not really different from the comparison between software and hardware, right? So again, using my favorite example of this AlphaGo algorithm, obviously doesn't have like a physical body, right? It's not a robot you see in sci-fi movies. What you see here is these expressions of the algorithm, the fact that this invisible artificial intelligence can actually play a very, very sophisticated game and can beat the #1 human player in the world, right? So that's quite something. That's quite extraordinary. And however, obviously, we don't see the hardware behind this algorithm. So this is what's called a tensor processing unit, or TPU. So it's not commercially available, and Google uses it for its very experimental projects, such as this one, which requires very high level of computing power. And you can further deconstruct the system and see all the circuit boards involved, right? So imagine like these are the brain tissues we can actually see and visualize and break down and study under microscope. So again, imagine a case when if I walk into the server room and I use a hammer and destroy all the hardware, so obviously this amazing algorithm is not gonna work, right? So that would be similar to the case of, let's say, if someone has a accident, physical brain trauma, okay? Then obviously the person will develop a wide spectrum of symptoms. On the other hand, the system here, the hardware here, could stay completely intact, right? As your computer, the hardware, all the circuit boards can be completely intact, but there could be a bug in the software which would still disable you from using the system, right? From the system to stop the system from functioning. So there are really two ways to cause the dysfunction of the system, which is very similar to human disorders. If you think about the fact that obviously we can have a stroke, right, destroying the hardware, and then subsequently you have a wide spectrum of mental disorders. But in many cases, you don't actually see physical damage to the brain. And this is why exactly we need to understand the computation, the algorithms of the brain, and how they might go wrong. Okay, so just to give you an overview of the landscape of computational psychiatry. Sorry about the slides. I think there's a bug from Mac to PC, but hopefully you can see, very good, very timely example of how softwares can go wrong. I think at this conference, you've already heard a lot about the second approach, which is the data mining approach, right? So things like machine learning, artificial intelligence, generally falls under this category. And the approach here is really to try to collect as much data as possible, right? So the more data, the more power you have, and the more likely you're going to get some sort of hit, a genetic hit or a brain marker hit. Today, I will really be spending the rest of the talk sort of describing what happens at this top level, so theory-driven approach, which is really sort of the most original way of doing science, if you think about it, right? We start with a very precise, well-validated theory, and in this case, mostly a computational theory, and then we actually design experiments to test these theories properly. And for this approach, we can also do, either cognitive modeling, so computational modeling of behavior and cognition, or you could model neural circuits and neural activity directly. And I think to emphasize the importance of the first approach, theory-driven computational psychiatry, I'd like to quote Henri Poincaré, who is a French mathematician, who famously said that science is built of facts as a house is built of stones, but an accumulation of facts is no more a science than a heap of stones is a house, right? So I think we also need to appreciate the fact that, even with lots of data, we still need a structure to this data, right? And in machine learning, people would, very famously say, if you have garbage in, you have garbage out. So even when designing a machine learning study or sort of data mining study, you still need to think about sort of the theoretical constraints of your data collection and your hypothesis space. But obviously for, if you're trained more like me, sort of from more basic neuroscience, you would really appreciate this statement here. And I think it's really a good quote for all of us to remember. And there's actually a lot of debate on this topic recently, and I would recommend this paper actually written by two economists, recently published, to sort of really discuss a deeper problem of our field, which is the lack of deep theories and a lack of overarching theory. Okay, so what are the pros and cons of this approach? So obviously it is mechanistic, right? It really helps us fight our intuition. Many times our intuitions are wrong, we have to admit that. It's also less expensive, so that's good, right? You don't have to have 20,000 participants in your study. You can actually design a very small study of 30 or 50 people if it's based on a very tight hypothesis. But obviously, the drawback is that it really requires a lot more training. I think our educational system these days is really more inclined towards creating data scientists, which is, again, not a bad thing, but I think it probably takes more time and effort to educate and to cultivate critical thinkers. And for clinical purpose, this approach obviously is a bit slower, right? It usually takes more time to derive the theory, to have the theory, design experiment, find the mechanism, and think about how that might inform your clinical practice compared to, machine learning, which is very practical, very pragmatic. And the good news is that there is recently, a really big trend, especially, again, talking about high-impact journals. They all pretty much support this approach. So there has been a series of studies. Some of you might be familiar with this one. And this paper on autism actually uses exactly the same model as the previous science paper on psychosis. And then my work has mostly focused on sort of looking at beliefs, and mostly worked with addiction. But again, hopefully by end of the talk, you'll see that my interest is quite broad. And this is because I think belief is really core to all of psychiatry, right? So essentially, psychopathology almost equals broken beliefs. Like obviously, a very obvious example is psychosis and schizophrenia, so delusional beliefs, right? That's very salient hallmark of this disorder. And obviously, we also know that drugs can elevate symptoms for any disorder you name it. It usually does not fix these broken beliefs, right? Which tells us that psychotherapy is still quite important, because that's really the goal of the psychotherapy. Okay, and number 3 is that even if you don't care about any of that, as a practicing clinician, you probably would appreciate this point that patients' beliefs in you and the treatment itself can actually impact clinical outcome and clinical practice. An example I would give here is that this study showed if patients, before the treatment starts, if the patient actually had very weak belief about if the treatment is going to work for them, they don't even stay in the study, right? So if you have a clinical trial, let's say for 8 weeks or 6 months, I would actually recommend generally as a good practice to measure your patient's beliefs at baseline. So how strongly they believe this is going to help them, and how much trust they have in you as a physician probably as well. So if they have very weak beliefs, it's very likely that they don't even stay with the study or the treatment. Okay, which brings to my next point, that it's probably quite important to manage people's beliefs systematically, right? So we designed a study to look at this effect, to see if we can actually manipulate or manage patients' beliefs about drug. But in this case, unfortunately, it's not really a treatment. The drug we chose was nicotine, because we kind of avoid sort of all the problems of running clinical trials in the US. As you know, it's very cumbersome. And the study goes like this. So these are all heavily sort of addicted smokers, cigarette smokers. So they come to the lab, we give them a cigarette to smoke, and as usual, we have either a placebo or a real cigarette, right, with nicotine. So that's your typical placebo-controlled design. But on top of that, we also manipulated their belief about the content of nicotine in the cigarette. So in other words, we had a 2x2 factorial design. We had the belief could be told yes nicotine or told no nicotine, and the actual content of nicotine could also be yes or no, right? So 2x2. And each smoker came 4 times actually, so within subject design, which is more powerful, but it was very painful to do, obviously. I won't go into the details of how we actually managed to do the study, but we collected a total of 24 smokers in our final sample. And after this procedure, they go into the scanner, and we give this really fun task for them to do. Actually, everybody loved the task, and they even refused to get out because it was just so interesting compared to all the other experiments they've involved to, like, watching like checkboards. So this is almost like a game, right? So basically, they see this exact visual. It represents a simulated stock market, right? So I don't know if you invest in stock markets, but the point here is that obviously if the market goes up, you want to invest more, right? And if you think the market is going to go down, you try to invest less. And subject's task is basically to decide whether to invest or how much to invest from 0 to 100% of their total portfolio. Okay, so it's a very engaging task. That's good. But what does it measure? We actually have done a series of experiments prior to this one to demonstrate that this task sort of engages a few what's called reinforcement learning signals, so signals such as reward and value, and also prediction error, which are known to drive our decisions, to drive people's choice behaviors. And there's also a huge animal literature on this, sort of showing the involvement of the dopamine system in computing these signals, right? Okay, so that's great. And essentially, we really want to see if the manipulation of beliefs, the manipulation of beliefs actually, as well as the impact of nicotine, can change these signals, right, that we know activate the brain's dopamine system. Okay, so here's what we see. So first of all, just to answer your potential question, there was actually no placebo effect. So placebo didn't work because these are very experienced smokers. They didn't know whether there was nicotine or not. However, the interesting fact existed in the two nicotine conditions, right? Remember, there are two visits. They both got nicotine. But for one condition, they were told there was nicotine, right? So in this condition, we saw like this very nice ventral striatal activity that encoded these reward learning signals. And that's great. That's kind of a validation check, a sanity check, because we saw this signal over and over again in many different populations, including healthy controls, and when smokers smoke a nicotine and believe there was nicotine. However, the interesting fact sort of surfaced when we look at this other condition. When they smoked exactly the same amount of nicotine, but thought there was no nicotine in the cigarette, the brain looked like this, right? As if belief itself erased the impact of nicotine on the brain. And obviously, this was actually one of my postdoc projects. And as a postdoc, working really hard for 12 hours a day, I really doubted my decision at this point. I was thinking this cannot be true, right? No one has ever seen such a dramatic effect. And I don't believe that a simple belief can really change the brain in such a dramatic way. However, we then also directly modeled behavior, which then sort of confirmed the neural result. So you can see this index here represents how important these reward learning signals are on my choice behavior. Okay, so that's kind of in the same direction as the neural results, right? In the sense that when you think there is no nicotine, but smoke nicotine, the behavioral effect of these signals was also significantly reduced. So conclusion of the study is that one obviously demonstrates the importance of doing computational modeling, but also very interestingly, I think that we can now look into the brain and see that beliefs, right, a very subjective construct, can actually override the effect of a very powerful neuroactive substance, such as nicotine, right? And I think that would have implication, obviously, for a lot of treatment studies. But I would like to use the last few minutes to really show you actually some work in progress, which I'm actually more excited about because we're moving more towards sort of the social cognition space now, social neuroscience. And we're now really looking at how people perceive themselves or what their beliefs are about their level of control during a social interaction. So this particular experiment, we modified a famous behavioral economics paradigm called the ultimatum game. So it's a very simple rule. Basically, the subjects always place this red person here. Okay, the subjects place with these simulated partners. Each partner come to you and say, okay, here's $20. I'm going to offer you $5, and I get to keep 15. Do you accept or reject? So if you accept, then you get 5, and I get 15. But if you reject, the deal is off, okay? So nobody gets anything. That's why it's also called take it or leave it, right? So very similar to business negotiations or many other professional occasions. So anyway, we modified this game so that in this critical condition, what we call the in-control condition, when the subject says no, that reject the offer, that's a signal, it's social signaling to the partner, right? Saying that I'm not really happy with this $5, I want more. So in response, the partner in the next round would offer more money. Therefore, the subject's action actually had impact on partners' behaviors. So if the subject said, no, I reject, then the next offer will increase by either $1, $2, or nothing in a probabilistic way. And if I say accept, that means I'm happy with $5. Okay, so maybe you develop a reputation of being cheap, okay? Maybe you want to test my water and see, okay, can I give you $3? Can I give you $2, right? Right, you should take advantage of that. If that's the case, then the next offer would decrease by either $1, $2, or nothing, probabilistically. Okay, so in this way, the subject will learn that their actions actually can impact future interactions. They should really learn to leverage this power they have, right, to gain control in the interaction. And obviously here, reputation matters, right? And you should play hard to get. It's almost like a dating situation, right? So play hard to get, okay? But not too much, okay? Because you might lose all your opportunities. So in this case, each rejection, remember that each rejection would actually cost you, right? Cost you losing the amount of money you could have got on that trial. Again, similar to real life situations. When you reject, you don't get that person, even if that person is not your ideal mate. Okay, so to come up with a control condition, we pretty much sort of take away this association here and just scrambled or randomized all the offers. In other words, the participants' actions had absolutely no impact on their partners' behaviors or offers in the next trial. So we call them in control and no control. Okay, so one very sort of soothing experimental finding here is that these are healthy controls. So they, on the group level, they all manage to influence their partners, right? You can see this is the actual offers they received. So the blue line is when they're in control. Everybody started with the offer 5, but they all managed to push up the offer kind of steadily. Okay, so that's very good, because this relationship is actually hidden. We didn't tell them at all that they could do this, but they managed to learn that. And another thing we measured here is their belief, their subjective belief about control. So after each condition, and also very interestingly that they did perceive a stronger sense of control for the in-control condition when they're supposed to feel strong level of control compared to the no-control condition. But also just look at all the individual differences here, right? It's massive. So there are people in the in-control condition that felt 0 level of control, right? These might be very depressed people, although we did exclude clinically depressed patients. Versus here, right, this is what I call the illusion, right? So the illusion of control. And especially these guys, maybe not surprisingly, these are, the study was done in Texas. So there are a lot of people with very strong sense of control, even when they absolutely had no control. Okay. All right. So we were in the process of replicating this in New York. It'd be interesting to see some cultural differences. Okay. This is actually my last slide for the results. Again, as I told you, it's work in progress. But I really want to show you here is the fact that we can use a quantitative model, and I won't go into the details of this model, but a quantitative model to actually proxy or simulate what participants are actually doing in this case. So here we assume, right, again, think about the game. If you are really smart, you shouldn't be thinking about just the current interaction, right? It's like playing chess. You have to think several steps ahead. So this is basically the computational model we came up with based on, again, a rich literature from computational neuroscience on what's called model-based planning. So here we can assume that, oh, maybe I'm only planning for tomorrow, or I'm planning for the day after tomorrow, or the day after tomorrow, right? So you can come up with different planning steps. And it turns out that most human beings in this case planned 2 steps ahead, which is not bad, right? Quite good, actually. People don't just think about what's going on right now. They're actually actively planning in the game. And interestingly, from this model, we can derive a computational parameter, what we call delta, but it represents the amount of controllability the participants had or thought they had. So what we call estimated controllability. And it's quite interesting in the sense that we can get one estimate for each condition, and it turns out that the people who scored very high in the no control condition, right? So these are the people, again, with very strong illusion of control, actually had lower controllability when they are given the power to control, right? So when they are in real controllable environments. So I think, like, obviously we can discuss what this might mean for mental disorders, and we also have neural data, which is still being analyzed right now. But I think even just based on the results I showed you today, it seems like this illusion of control would negatively impact your behavior, your ability to perform optimally in a situation when you really should. So belief could be, a subjective measure, but now can be modeled computationally. Okay, so I want to stop here since my time is up. And just to bring up this last slide again, and hopefully I've convinced you to some extent that computation is important, to think in computational terms. And obviously there's a lot we need to do for the field. We need actually to have more empirical papers. We need to what I call democratize computational psychiatry, in the sense that so far the research has been done by a relatively small group of people. We also need to change people's mindsets. And if you want to learn more, there's a course I organize. If you fancy to coming to New York City to listen to computational psychiatry and enjoy some art, we're very grateful to the Metropolitan Museum of Art for letting us host it there. Again, you see some familiar names here. Dr. Renee Kahn is also one of the speakers. And to find out more, you can go to this website. Thank you. Yeah.
Wow, fantastic. This is really opening Pandora's box and extremely inspiring and well within time. So we have time for 1 or 2 questions. This was so well explained, you must have questions.
There's one there.
Where?
There.
Ah, yes.
Thank you so much, Rutger from Psychiatrie, the Netherlands. I was wondering if you're trying to correlate phenotypical aspects of the human mind, so inner experience and overt behavior, to physical processes, as you say, the brain. Don't you think it requires a very, very detailed operationalization of the human phenotype first? You need to find out what to correlate to what in order to do that.
Exactly.
And
yeah.
how would you tend to approach that matter?
Yes, exactly. That's why, I think that this theory-driven approach, especially computational modeling of behavior and cognition per se, is quite important. And obviously today I don't have the time to give you the whole landscape, but deep phenotyping is meant to address that exact question. And so it is being sort of, studied by a lot of groups. Yeah.
Is there more? It's very hard to see in this large. Shout if you have a question. Is there a hand there? No?
It's very clear.
Okay. Well, I have one question.
Sure.
Could you also reverse the argument that you actually need computational psychiatry to actually be able to study things like belief, instead of the approaches before with cognitive neuroscience or?
Yeah, obviously, I think a more so-called objective way, right, to define belief would be computational modeling. However, like I think you'll notice that we still use, subjective reports even in our work, because I think that's still a very important source of information, and which distinguishes human subjects from animals, right? Is the fact that we can actually report our subjective states. So I think that because it's such an infant stage of this line of work, I do think that, I don't want to completely sort of ditch like the old approach of subjective reports, but if you can match that with some sort of computational model and parameter, that would be ideal.
Complementary.
Yeah.
Yes. Well, fantastic. Thank you so much again.
Thank you.
Yeah, put it there. Yeah. Thanks.